Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Evolution of Earth's atmosphere. The Sun, the Earth, and other planets of our solar system were formed when matter coalesced from a rotating nebula approximately 4,567 million years ago. The atmosphere of the Earth has been changing continuously since its formation. The Earth's atmosphere has a thickness of about 100 kilometers, but above 35 kilometers from the Earth's surface, the air pressure is so low that water cannot exist in liquid form. The habitable zone is within 5 kilometers from sea level. The highest city in the world is La Rinconada in Peru at an altitude of 5,100 meters, 16,700 feet, which has an economy based on gold mining. This city is at about the same elevation as Mount Everest Base Camp. The air at this altitude has only 11% oxygen compared to 21% at sea level. The nebula that produced our solar system originated from the explosion of older stars containing heavy elements like iron. The accumulation of mass at the center of the rotating nebula was so large that gravitational compression initiated the fusion of hydrogen into helium, thus giving birth to our Sun. The planets orbiting the Sun formed by accretion. The heavier elements concentrated in the cores, and the lighter gaseous elements became the atmospheres. The most abundant chemical elements in the Sun are hydrogen, 73.5%, and helium, 24.9%. All other elements are in concentrations of less than 1%. The atmosphere of Jupiter, which is the largest planet, is mostly hydrogen with about 10% helium and small amounts of other gases like methane, ammonia, hydrogen sulfide, and water. These compositions indicate that the nebula from which our solar system originated was mostly hydrogen, helium, and small amounts of heavier elements. The small planets Mercury, Venus, Earth, and Mars lost their hydrogen and helium rapidly because their gravitational pull is not strong enough to retain these light elements. Further away from the Sun, where it is much colder, methane can condense as a liquid, and Saturn's moon Titan has a predominantly nitrogen atmosphere with pools of liquid methane on its surface. When the material forming the Earth coalesced and melted, it organized itself into layers with dense materials at the core and less dense compounds closer to the surface. The gases comprising the atmosphere formed the outermost layer and had a composition similar to the gases of the condensing planetary nebula. During the Hadean Eon, the Earth's surface consisted of molten rock, a magma ocean, and water existed only as vapor in the atmosphere. Hydrogen and helium were lost early in the Hadean Eon due to Earth's weak gravity. The circulation of molten metallic iron-nickel alloy in the core of the Earth established the magnetosphere, a region in space where the motions of gas and fast-charged particles are controlled by the magnetic field of the Earth. The magnetosphere deflects most solar wind ions before they penetrate the atmosphere, but the charged particles which are not deflected are directed toward the Earth's magnetic poles, where high-energy collisions with atoms of the atmosphere produce an aurora light display. Around 4.45 billion years ago, the Earth experienced a violent collision with a planetoid called Theia that was about the size of Mars. The impact added extra mass to the Earth, but a portion of the impact debris went into orbit and accreted to form the Moon. The Great Collision sent much of the atmosphere into space, but most of it remained within the Earth's gravitational field and was recaptured when the debris from the giant impact cooled and was partitioned between the Earth and the Moon, giving them similar crustal composition. Earth's Hadean atmosphere had methane, ammonia, water vapor, and small percentages of nitrogen and carbon dioxide. A cataclysmic meteorite bombardment around 3.9 billion years ago kept much of the Earth's surface in the molten state, and the incoming impactors may have brought additional water, methane, ammonia, hydrogen sulfide, and other gases that supplemented the atmosphere. The high surface temperature of the Earth during the Hadean Eon favored the depletion of atmospheric methane through the endothermic reaction of methane with steam in the atmosphere. The resulting carbon monoxide readily combined with metals to form carbonyl compounds. The Hadean Eon was too hot for liquid water to condense on the surface of the Earth, but water vapor would have been able to condense at high altitude in the atmosphere and produce rain that evaporated quickly as it fell when it approached the ground. Toward the end of the Hadean Eon, volcanic activity started increasing the percentage of carbon dioxide in the atmosphere. The Earth's surface changed from molten lava to solid rock, and liquid water started to accumulate on the surface. The crust of the Earth started to cool down during the Archean Eon. The amount of water vapor in the atmosphere decreased as water started condensing in liquid form. Continuous rainfall for millions of years led to the buildup of the oceans. As steam condensed into water, the atmospheric pressure of the Earth decreased, and liquid water dissolved gases like ammonia and removed them from the atmosphere by creating ammonium compounds, amines, and other nitrogen-containing substances suitable for the origin of life. Liquid water changed the chemistry of Earth's surface. Water combined with gases such as sulfur dioxide to produce acid rain that created new minerals on the Earth's surface. Volcanic carbon dioxide peaked during the Archean Eon and started to decrease through the formation of carbonate minerals that resulted from reactions of metals with the carbonic acid generated from carbon dioxide and water. Microfossils of sulfur metabolizing cells have been found in 3.4 billion-year-old rocks, and it is known that the first aquatic photosynthetic organisms originated around 3.5 billion years ago. The oxygen produced by cyanobacteria, blue-green algae, during the Archean Eon reacted with metal ions in the anoxic sea. Billions of years would pass before the photosynthetic microorganisms could eventually change the composition of the atmosphere. By the middle of the Archean Eon, the Earth had cooled enough so that most of the water vapor in the atmosphere had condensed as water, and the Earth had its first days without clouds. Ammonia and methane were only minor constituents of the atmosphere. Carbon dioxide comprised about 15% of the atmosphere, and the percentage of nitrogen was 75%. Most of the original components of the atmosphere had escaped the Earth, precipitated as liquids, or reacted chemically to form solid compounds. Volcanic activity and the photosynthetic bacteria were now the major factors influencing the Earth's atmospheric composition. Monocellular life proliferated during the Proterozoic Eon. Anaerobic microbial life thrived during the beginning of the Proterozoic Eon because the Earth had little oxygen. Anaerobic organisms do not require oxygen for growth. They obtain their energy in various ways. Methanogens combine hydrogen and carbon dioxide to produce methane and water. Sulfate-reducing bacteria get their energy by metabolizing methane and sulfate radicals. Organisms capable of photosynthesis, such as the cyanobacteria, use the energy of sunlight to convert abundant carbon dioxide and water into carbohydrates and oxygen. Oxygen was deadly to the anaerobes, so this gave photosynthetic organisms a competitive advantage. By the first quarter of the Proterozoic Eon, the sun had become brighter and its luminosity had increased to 85% of the present level. By this time, most of the carbon dioxide had been depleted from the atmosphere, leaving nitrogen as the main atmospheric gas with a small percentage of oxygen. Nitrogen gas, which is quite inert chemically, had been a small percentage of the Earth's atmosphere during the Hadean Eon, but it became the major component of the atmosphere during the Proterozoic Eon once all the other gases were gone. Photosynthetic organisms had been releasing oxygen since the Archean Eon, but the oxygen was immediately depleted by the oxidation of metals. An increased period of oxygen production occurred between 2.4 and 2.0 billion years ago and is known as the Great Oxidation Event or the Oxygen Catastrophe. The higher oxygen level created banded iron formations by precipitating dissolved iron as iron 3 oxide. Enough free oxygen accumulated in the atmosphere to kill anaerobes near the Earth's surface and created an opportunity for the development of aerobic life forms. Starting around 2.4 billion years ago, oxygen molecules migrated into the upper atmosphere and formed an ozone layer. This is a region in the stratosphere located between 15 to 35 kilometers above the Earth's surface, where oxygen molecules, O2, are converted to ozone, O3, by the sun's ultraviolet rays. The reverse conversion of ozone back to oxygen releases heat. The ozone layer basically absorbs high-energy ultraviolet radiation and converts it to heat. The high-energy ultraviolet light is dangerous for life because it can cause mutations in DNA sequences. During the last billion years of the Proterozoic eon, the Earth's atmospheric composition was very steady with approximately 10% oxygen. At this time, soft-bodied multicellular organisms developed. By 850,000 years ago, the minerals in the sea and the land could not bind much oxygen, and the excess oxygen began to accumulate in the atmosphere. With the increased oxygen levels and the protection of the ozone layer, organisms capable of aerobic respiration could now proliferate all over the surface of the Earth. The Cambrian period at the beginning of the Phanerozoic eon is marked by the abundance of multicellular life. Most of the major groups of animals first appeared at this time. Vegetation covered the surface of the Earth, and oxygen comprised 30% of the atmosphere. Air enriched with so much oxygen allowed giant insects to develop and caused frequent forest fires set off by lightning. A great mass extinction event occurred 251 million years ago, marking the boundary of the Permian and Triassic periods. Oxygen levels dropped from 30% to 12%, and carbon dioxide levels reached about 2,000 parts per million. This was Earth's worst mass extinction, and it eliminated 90% of ocean dwellers and 70% of land plants and animals. This mass extinction was caused by a series of volcanic events in Siberia that lasted for about 1 million years and released large volumes of carbon dioxide and gases containing sulfur, chlorine, and fluorine. By 228 million years ago, oxygen levels had risen to about 15% of the atmosphere, and the first dinosaurs appeared. Oxygen levels continued to increase, and by the end Cretaceous, 100 million years ago, oxygen had risen to about 23% of the atmosphere. At this time, dinosaurs were well established, and modern mammals and birds began to develop. For the last 100 million years, the percentage of oxygen has fluctuated between 18% and 23%. The Earth's current atmosphere contains about 78% nitrogen, 21% oxygen, 1% argon, and 400 parts per million of carbon dioxide. The combustion of fossil fuels has been generating large quantities of carbon dioxide since the start of the Industrial Revolution and continues today at a very high rate. Mammals, including humans, can only live within a very thin layer of the Earth's atmosphere. We should keep our air clean so that we can live in harmony with nature. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.